Hi, everyone. And this have to evaluate integrals. So what strategies do we have? So oftentimes we start off learning the integrals that we can just immediately apply anti-differentiation to. So we can just immediately go backwards using our derivative rules. So for example, the integral of cosine is sine plus c. So if we can't just immediately apply an anti-differentiation rule, we have two choices. So we can either simplify the integrand before applying an anti-differentiation rule, or we can perform u substitution. But sometimes more than one method can work for us to solve and evaluate the integral. So let's just jump into this first example. So we are evaluating the integral of x plus 1 all squared dx. So first we can try to simplify this. So if we're going to simplify, we can rewrite the integral of x plus 1 squared dx, and we can just square that integrand. So remember, what I'm highlighting here, this is called the integrand, and it's just the function that we're taking the integral of. So we can simplify that integrand, so we can just square it and get x squared plus 2x plus 1 dx. And now, instead of integrating a composition of functions where we have x plus 1 and inside of x squared, we're integrating a polynomial function, and we can just integrate this term by term. So we can integrate x squared, we can integrate 2x, and we can integrate 1. So this splits to integrating term by term. So we remember that we can integrate x squared using the power rule. So we add 1 to the power and divide by that new power. We can integrate 2x so that 2 stays. And then again, we add 1 to the power of x and divide by that new power. And we know that whenever we integrate 1, we just get an x. And because these are indefinite integrals, meaning they don't have bounds, now we're just going to add c. So we can simplify this, and I'm just going to pull these coefficients in front. So 1/3 x cubed. I notice that my 2's are going to cancel out, so then I'm just left with x squared plus x plus c. So this is one way. We can simplify the integrand by just performing the operations that are present there. In this case, that's squaring x plus 1. And then we end up with a polynomial that we can integrate term by term, applying the power rule. Otherwise, we can use substitution. So like I said, this is a composition of functions. So we can use u substitution. So I'm going to highlight here, my inner function is this x plus 1. So whenever we see functions inside of one another, this is often denoted with using parentheses in some way, but we can see, okay, my x plus 1 is in parentheses, so that's going to be my inner function in substitution. And then the next step to applying substitution is to take the derivative of both sides. So the derivative of x is 1, the derivative of 1 is 0, and then we're going to want to solve for dx. So I'm just going to multiply by dx on both sides to get that du equals dx. So this is one way to apply substitution, and whenever we do this, we're treating this du over dx as if it's a fraction. So your instructor may not want you to solve it this way. If they don't want you to solve it this way, they probably have made that clear by telling you this isn't a fraction, and for most purposes, it is not a fraction, but we can use it, we can abuse our notation a little bit and treat it like a fraction to help us solve our problems. So now we rewrite our integral. So we start off with the integral of x plus 1 squared dx. We rewrite this as the integral of u squared du. So we rewrote the x plus 1 was our u, and we rewrote this dx is our du. So we rewrite this, and now this is something that we just apply the power rule to. So we are going to add 1 to the power, divide by the new power, and add c. And one thing, whenever we apply substitution, is we always want to leave our integral as we found it, meaning that we were given the question in terms of x, and we want to give an answer in terms of x as well. So I'm just going to write this as 1/3 x plus 1 cubed plus c. And these are our answers. So I'm going to go ahead and put each of our answers into a box. And at first glance, these are not the same. We don't have the exact same thing written in each of these boxes. So at first glance, it may not seem like these answers are the same. However, if we expand out our answer in our right-hand box, we can see that these actually are going to be the same. So I'm just going to go ahead and multiply this out for us. So this is going to be 1/3. And then x plus 1 cubed is x cubed plus 3x squared plus 3x plus 1. And when I distribute that 1/3, I have 1/3 x cubed plus x squared plus x plus 1/3. Okay, so what we can see is that whenever we multiply out the right-hand side, we get the same thing. So I'm going to go ahead and highlight these first 3 terms in yellow and these first 3 terms in yellow, and we can see that these are the same. So they're going to differ by 1/3, but that 1/3 is our constant that we can see there, the plus c that is not highlighted. So we can see that these actually do give us the same answer, even though it may not look like it. So if you're working questions with a friend and they get an answer that looks different than yours, check and see if you use the same method to solve that integral. If you use different methods, your answers may look different, but actually end up being the same. And by the same, I mean that those answers may differ by a constant, but that's okay because we have a plus c to account for differing by constants. So let's look at another example. So we're integrating x plus 2 times x squared plus 4x. So again, on this left-hand side, we're just going to multiply this all out. So remember, we do not have an anti-differentiation rule that undoes the product rule. So we have lots of ways in which we can undo the derivative rules, but remember that in Calculus 1, we do not have a method to undo the product rule via anti-differentiation. So that means that if we're given a product, we cannot apply anti-differentiation, and we have to either substitute or simplify. So let's start with simplifying. If we have this integral of x plus 2 times x squared plus 4x, we can just FOIL everything. So that's what I'm going to do. So this is the integral of my first, give me x cubed, my outside gives me 4x squared, my inside gives me 2x squared, and then my last give me 8x. And this is going to be x cubed plus 6x squared plus 8x. And remember, I just get these by combining my like terms. Now we can split up just like before, and we can integrate this term by term. And I'm also going to factor out my coefficients out of my integral, and that's applying an anti-differentiation rule that we know. Okay, so now we just apply the power rule to each of these. So remember that I'm going to add 1 to my power, divide by my new power, add 1 to my power, divide by my new power, add 1 to my power, divide by my new power, and then I add a plus c on the end. So now we can cancel some things out and rewrite. So the 6 and 3 cancel out to give me a 2. And my 8 and 2 cancel out to give me a 4. So this is going to be 1 over 4x to the 4th plus 2x cubed plus 4x squared plus c. Okay, I'm going to go ahead and put this answer in a box. So this is our answer. Actually, I'm going to leave that answer just like it is. And now we can move on to substitution. So, like I said, if we have an integral of a product, we have to either substitute or simplify. So although it may not seem like we can use substitution here, one thing that I notice is that the derivative of x squared plus 4x is a multiple of x plus 2. So one way in which we know that we can substitute is if we see we have multiple expressions in our integrand where one looks like the derivative of the other. So we see this oftentimes in natural log, but we can also use it here. So I'm going to put u equals x squared plus 4x, because when I take the derivative, I'm going to get 2x plus 4. So like I said, we can notice that this is 2 times x plus 2, which is going to help us cancel things out. But for now, when we apply substitution, we're just going to solve for dx. So I'm going to multiply by dx on both sides. And then I'm going to divide by 2x plus 4 on both sides. Okay, now I have what I need to rewrite my integral. And 2 times x squared plus 4x dx, it can rewrite as the integral of x plus 2. And then I'm going to substitute my x squared plus 4x as my u. And then my dx is du of x plus 4. So that's what I did here. Okay, so now remember that whenever we are using substitution, we need to make sure that all of our x's come out of the integrand. So we're using substitution to change from an integral with all x's to an integral with all u's, which means that for this to work, all of my x's have to cancel out. So in order to do that, I'm going to rewrite this 2x plus 4 as factoring out a 2 to now give me x plus 2, and that will allow me to cancel out all of my x's there. So now I'm going to be left with, I'm going to pull that 2 in front to be a 1/2 u du, and now I just apply my power rule. Add 1 to the power, divide by that new power, add c, and I get 1/4. Remember, leaving it how I found it, x squared plus 4x squared plus c. So again, I'm going to put this one in a box. And again, at first glance, these do not look like they're the same answer. However, we can rewrite the answers to look the same. So again, I'm going to rewrite that answer on the right-hand side, 1/2 x squared plus 4x squared. So I'm just going to keep my 1/2 in front. My first terms give me x to the 4th. My outside terms give me 4x cubed. My inside terms give me another 4x cubed. And my last terms give me 16x squared. I'm going to combine my like terms in my middle. So I have x to the 4th plus 8x cubed plus 16x squared. And lastly, I'm going to distribute that 1/4 to each term. So again, highlighting in yellow, we can see that these terms, these expressions are now the same, and then we're going to have that plus c on both sides. So they can differ by a constant, but all of the x terms need to be the same. So like I said, if you're working questions with a friend and they have a different answer than you, check to see if you solve the integral in the same way or not, because depending on the method they use, they may have an answer that looks different, but turns out to be the same. This is how we can use 2 different methods to solve the same integral. Not all integrals are going to be able to be solved using 2 methods, so just keep that in mind when you're going through. Some of them, not many, can be solved 2 ways, but that may explain why your answer looks different than someone else. We hope this helps, and good luck.